Good afternoon, everyone. A warm welcome to you all. We are indeed today happy and also honored to have amidst us Professor Pavol Hell from Simon Fraser University, a renowned mathematician and a computer scientist with us. On behalf of the Institute, we would like to extend a warm welcome to Professor Hell, and then we have a small felicitation. We request our Vice Chancellor Maharaj, Revered Swami Sarvottomananji Maharaj, to hand over a bouquet to our guest speaker. May I request Professor Sumit Ganguly, who has come from IIT Kanpur, to hand over this. Now, before we dive into the talk, it's my honor to actually introduce the guest speaker. Professor Pavol Hell is a faculty of computing science at Simon Fraser University, Burnaby, Canada. He received his PhD from the Université de Montréal in 1973, long way, under the supervision of Gert Sabudussi. I don't know if I pronounced it right. And in his PhD research, he pioneered, on the suggestion of his supervisor, the study of graph retracts. He describes his area of interest as computational combinatorics, which includes algorithmic graph theory and complexity of graph problems. His current focus is on nicely structured graph classes and on the complexity of various versions of graph homomorphism problems. He has co-authored a book titled Graph and Homomorphisms alongside with Yaroslav and published numerous academic papers, and his citation count in Google Scholar is more than 10,000. So without further ado, I request our guest speaker to address you all, but I am sure like most of you already have hinted me that it's too daunting, the topic itself. But don't worry, he will start with the basics and then at least he will introduce the topic to us, what exactly is the problem. If time permits and if you are interested, he can get into some details as well. So as you all know, the title is A Graph Theory Perspective on the Quest for Dichotomy. So over to you, sir. I now request Professor Pavol Hell to address the gathering.
I'll try to speak in the microphone, but I hope you can hear me when I walk back and forth, because I'm used to talking and walking and sort of tying me here. But if I have to push buttons here, then I guess I will have to stand here. So this is how I forward. Oh no, I get something here. Perfect. Okay, I'll try. Okay, so it's an introductory talk, and I sort of try to set up the general background and reminder about this history going back to prehistory, when in the 1930s mathematicians and logicians, philosophers started asking themselves, what exactly is an algorithm? That was Hilbert's program, Hilbert's problems. Some had to be solved by algorithms, some to prove that algorithms could not exist. So, you know, then these people came and proposed formal models of algorithms. Big surprise, they all turn out to be equivalent. So there is really this concept that's general. And the language we will use, you could talk about it in many different ways. but let's think about it as decision problems. So the problems were sort of classified as decidable versus undecidable. I think maybe I'll just... you have a clicker now, then we're in business. Wonderful, thank you. I'm free. Okay. So there are examples of these kind of problems, even in graph theory. You know, any sort of typical optimization problem you think about in graph theory, like tree coloring, is an example of a decidable problem. There is an algorithm, you just try all possibilities. So just in case, if you don't know what tree coloring is, you want to assign three colors to the vertices of a graph so that adjacent vertices obtain different colors. That's okay for everybody, right? Good. So what was the other problem, the one that's not decidable? That's the neighborhood problem. In this problem, you have one graph, like a path. Well, if you look at the circled vertex, I don't know how to point, but if you look at the circled vertex and see all of its neighbors, and you look at a graph induced on those neighbors, that's the neighborhood of that vertex, right? So this graph has the property that every vertex has the same neighborhood. The path with three edges is the neighborhood of every vertex. I say that this graph realizes the path with three edges. And the question is, if I give you a graph G, like the path with three edges, is there a graph H in which every neighborhood is G? That turns out to be an undecidable problem. Even a simple question like that in graph theory can turn out to be... Yes? It should be a pointer there. I just don't know which button to push. I'm afraid to turn it off. Oh, okay. So never mind. That's fine. I think I can do without pointers, but having the ability to walk is much more important. So let's advance a little bit in history. In the 60s, people started to asking, okay, yes, we have algorithms for problems like tree coloring, but they're just too slow. You cannot color a graph with 10,000 vertices. So maybe we should distinguish between problems that are efficiently solvable and not efficiently solvable. And people formalized the models of what is efficiently solvable, that turned out to be algorithms whose running time can be expressed in as a polynomial of the input length. Those, I guess, two people that came independently to this conclusion were Jack Edmonds and Cobham, and they further divided the decidable problems into those that are tractable, have polynomial algorithms, and intractable. And in graph theory, the perfect matching problem is an example of a tractable problem. Does this graph, can the vertices of this graph be covered by disjoint edges so that every vertex is in exactly one? And that has a polynomial algorithm. In fact, it was Edmonds who first discovered it. And intractable. Even now, we still don't have one, right? There isn't one that we have. What we have are problems that we don't know whether are tractable or intractable, like tree coloring. We have algorithms for it. It's certainly decidable. But we don't have an efficient algorithm or a proof that one doesn't exist. By the way, I forgot to say, for the neighborhood problem, the proof that it's undecidable is to take a basic undecidable problem, I don't know, such as the halting problem or the tiling problem, and just reduce it to this problem. Translate it into a question about neighborhoods. But we don't have such tools for this. So outside of graph theory, intractable problems were found and proposed. These are some example papers. They're sort of artificial, but eventually less and less artificial. And they have one thing in common, and that is to prove their intractability, you go and say, suppose we have a solution. Suppose somebody gives me the answer. I just want to prove that this is really the answer, that it's a solution. That turned out to be the intractable part. So the logical question then is, what about problems which aren't like that? Problems which, if you give me the solution, I will be able to verify in polynomial time that's correct. Like if you give me coloring of the vertices of the graph, I just look at every edge and check that the colors are different, and that is polynomial algorithm. So this is a problem where solution checking is polynomial, but solution finding we don't know. And so they define the class NP as a class, the problems that have tractable checking. And then Cook and Levin, so again, two independent researchers in the 70s, both recognized that this propositional problem of satisfiability, say formulas in conjunctive normal form or whatever, plays a crucial role. Any problem that they found in the class NP could be written in this model, in this terminology. More formally, they proved that any problem that is in NP, that is polynomial checking algorithm, can be reduced to a formula that then you need to be checking the formula. So they recognize the crucial role of SAT. There are other problems that have this property, such as the subgraph problem. I give you graphs G and H, and I ask, is G a subgraph of H? That also has this property. And also in these papers, implicitly, the question that we today refer to is P equal to NP was identified. Maybe not explicitly, but it was mentioned in, for example, in Cook's paper. He asked specifically whether every problem with tractable checking admits tractable solving. That's the question, right? And today we refer to this as the big question of P equals NP and okay, anyway, this, I'm sure everybody knows this. I just wanted to set up to where we are going to go in these terms that you have heard before. Going through with the milestones, while Cook made this theoretical step, it was Karp who changed this abstract logic into practical computer science. Karp identified practical optimization problems, typical computer science problems that turned out to be also representing all problems in NP. I will tell you now, of course, that's what we call NP complete, right? If you have the property that every problem in NP can be reduced to this problem, then it's called NP complete, like the subgraph problem or the satisfiability problem. And Karp identified many others, including tree coloring, the Hamiltonicity problem, integer linear programming, and so on. Another important thing that Karp contributed was he went around North America giving lectures on this theory. What did he call it? It's a word that escapes me. Conceptual, I think, conceptual introduction to computer algorithms for mathematicians. That was the title of the talk. He gave one in 73, and then another one in 74, and I was lucky enough to hear that talk in 74. just finished my PhD. I was a postdoc with a logician, and he and I went down to San Francisco and listened to Karp's lecture, and I thought, this is really exciting, interesting topic. Now, Karp did another thing which has relevance for us because it was sort of the first dichotomy. Do I actually say it? No. So I have to tell you, this is a dichotomy you probably know, and that is for the problems of K coloring. K is sort of a parameter, right? And Karp was the first to observe, Karp was the first to observe that this problem is polynomial when K is 1 or 2, and NP complete when it's 3, 4, or more. So this is the dichotomy. As you vary the parameter, it splits into those easy problems, here K less than or equal 2, and those hard problems, K is at least 3. So my logician supervisor was then a well-known professor at Simon-Fraser by the name of Alistair Lachlan. And I was on the way home. Lachlan was busy. He was part of the organizing committee, or he belonged to some editorial board, and he didn't have time to go to these lectures. And I was telling him about this exciting new development. And then whether because he liked what I said or he found it in some other ways, he asked his student, Richard Lardner, to sort of ask this abstract question. This dichotomy, K less than or equal to, K greater than or equal to 3, is interesting, but if you think about it, there could be in this class of problems that have polynomial checking, other problems that are neither polynomial nor nor NP complete, or as abstract or as general as SAT. Okay, and Lardner proved, and this is a result that sort of sets up the stage for what we are talking about, that indeed in NP there must be problems that are neither polynomial nor NP complete. So if you think of the big world of NP, polynomially checkable problems, and the small world of polynomially solvable problems, there is in fact an infinite hierarchy of more and more complex problems, provided P is not equal to NP. If P is equal to NP, then they all collapse. But if not, there is a whole hierarchy. So Karp's dichotomy result then should be interpreted to mean, as far as coloring problems are concerned, this hierarchy does not exist, collapses. It's only the easiest or only the hardest. There isn't anything in between. So the next big development was the NP completeness book by Johnson and Gary and Johnson. I guess you all know that. By that time, I had my first real position at Rutgers University in New Jersey in mathematics. I liked this stuff, and I heard that someone from Bell Labs is going to give a grad course on sort of theoretical aspects of computer science, and I wanted to shift into computer science. So I attended that, and he sort of test ran the book there. That was really very inspiring to hear about it directly from him. So in 1978, the Symposium on Theoretical Computer Science had a whole spate of papers on this sort of dichotomic related questions, including a paper I wrote with David Kirkpatrick. I guess Sandeep knows. All these problems had in common that they proved dichotomies, or at least studied dichotomies asked questions about dichotomies in various sort of problems. In the paper that David and I studied, we asked the following question. So the perfect matching problem is polynomial. We already discussed that. Can you cover the vertices of a graph by disjoint edges so that every vertex is covered? What if you ask, can you cover the vertices of a graph by disjoint triangles so that every vertex is covered? Or if you want to have a graph G and you want to know whether your input graph can be covered by disjoint copies of G so that every vertex is covered. And we proved a dichotomy about that. Basically, it's only matchings and things that are related to matching. I won't have time to talk about all the others, but they're sort of similar flavor of dichotomy. Except I will say more about the paper of Schaefer. For that, I'm going to dive in a little bit into a little bit of more technical discussion, but if you don't follow all the details, don't worry, because we'll soon sort of abstract from that and talk about it in more general terms. So Schaefer was a student of Karp, and Karp asked him, okay, if SAT is such a nice problem, you should find other logic problems that have this property of being NP complete, of representing all the other problems in NP. Because if you want to prove a new problem NP complete, you need good tools to reduce to, right? SAT is a good tool, but maybe we should have others. And so he asked this problem in the general language. So S is a finite family of relations of finite arities. Think about having one binary relation and two ternary relations. And then for this parameter S, the problem is you are given a set with a corresponding family of relations on X. So S is a family on 0, 1. True, false, if you like. But the input has other ground set, a bigger set X. But the relations correspond. If my example S had one binary and two ternary relations, then X will also have one binary and two ternary relations. And you are looking for a mapping that maps the elements of S to 0, 1, so that if two elements of X are in the binary relation, their images are in the corresponding binary relation on 0, 1. And if three vertices are in the second, say, ternary relation on X, then their images are in the second ternary relation on 0, 1. Okay? So the relations are preserved. That's why the relations have to be in a correspondence. So I want to give an example. Suppose the ternary, we have one ternary relation on S, which consists of the triples 0, 0, 1, 0, 1, 0, 0, 1, 0, 0. I wrote them as strings, but they should really be sort of vectors. Bracket 0, comma, bracket, comma, 1, bracket. And so what about it? Well, the input now is a set, an arbitrary set, a finite set X, on which we have triples. Some triples are given on the set. And we want to assign values to the elements of X. Think of it as true and false, 0, 1. Every vertex, every element of X is either going to 0 or going to 1. And if we have a triple on the set X, we want the three images to be in the set S. So what do we want of the triple? We want that triple to be 0, 0, 1, 0, 1, 0, or 1, 0, 0. They could be anything as long as they're not all the same, right? So this is known as not all the same trisat without negated variables. It's a complicated name, but this is the problem. Okay. So that turned out to be, by the way, an important NP-complete problem. Not all equal trisat is used a lot for reductions. Here is another example. We have 3 binary relations. In the first one, 0, 0 is missing, but otherwise everything is there. In the second one, 1, 0 is missing, and in the third one, 1, 1 is missing. Okay. So if you impose, so you have an input with relations. Okay, so this is wrong. It should be R0, R1, R2, so that they correspond. Okay. You have you have a set X with 3 binary relations. If you impose the first binary relation on a pair, you are just saying they are not both false. That's like saying X or Y, right? The second relation is X is not false or Y is not true. That's like X or Y bar, so on. So this is just 2SAT. Okay. So this is a language that represents the satisfiability examples or the satisfiability variants that we know, but in general, any number of variants, anything could be described in this language. And then Schaefer listed what problems of this sort are known to have polynomial algorithms. So the trivial case is when every relation has the constant all true vector. If assigning all variables true satisfy every constraint, then the problem is trivially solvable. You say the solution is everyone is true. That satisfies all constraints. Similarly, if you can say mapping all vertices to 0, making all of them false, satisfies all the constraints you have given me, all the relations, then that's good. I have a solution. You know that 2SAT has a polynomial algorithm. This is sort of saying if you have a clause or a relation that says X or Y, and you know that you already know that X is false, then Y must be true. And you sort of propagate these implications until you either get a solution or get a contradiction. A more general version of this is Horn clauses. Those are basically clauses that are implications. This or this or this or this implies that. Those also have similar sort of propagation algorithm. And there is complementary version for the negated variables. So those are all sort of similar in spirit. The first 2 are trivial. You have a trivial solution. The next 3 are propagation. But there is a last one. And that is if the constraints, the relations you ended up with can be equivalently described by a system of linear equations modulo 2, then we can use algebra. You can use Gaussian elimination, whatever, to compute the solution in polynomial time, or to decide in polynomial time if the system has a solution or not. So those were all known, of course. They are just sort of carefully analyzing what models are possible in this terminology. But what Schaefer proved more importantly is if it's not these cases, then the problem is NP-complete. So here is a dichotomy. That was a very important dichotomy, much more important than the one that Kirkpatrick and I had, and had a big influence on this field of theoretical computer science. So except for these problems that have easy solutions, everything else is NP complete. So now let's switch back to graph theory. There was a sort of a parallel development in graph theory by coincidence, even though our paper on generalized matchings and Schaeffer's paper on generalized satisfiability were presented at the same conference. I didn't really clue in on the importance of this at the time. I wasn't at the conference. David presented the paper, but I had the volume. I looked at Schaeffer's paper. So here I repeat the dichotomy that Karp discovered and go on with other examples of similar dichotomies for graphs that also fit sort of the Schaeffer's mold, as we have seen. So one problem is cyclic K-coloring. In cyclic K-coloring, the colors are not just K numbers, but they are sort of cyclically ordered. And you are asking whether the input graph has a cyclic K-coloring, which means adjacent vertices get consecutive colors. Okay? So you can give an edge colors 3, 4, but not 3, 7. Okay? Adjacent vertices get consecutive colors. This turns out to be, so here is an example of what it looks like for cyclic 5 coloring. The circles are first all vertices colored 1, all vertices colored 2, all vertices colored 3, and the edge means there could be edges in between. There are, of course, no edges within, and there are no edges diagonally across. That problem turned out to be NP complete, except in the trivial case when k is equal to 2, in which case this is just 2 colors. Now there are other models, and I guess I probably will start skipping, but maybe I'll start skipping here. This is you colored by tuples rather than single colors. So the question is, can you color the graph with, let's say, pairs so that adjacent vertices obtain disjoint pairs? Adjacent vertices obtain disjoint pairs. And that turned out to be polynomially solvable in a trivial case when the graph is bipartite, and NP complete in other cases. Now, what all these three examples have in common is that those mappings are graph homomorphisms. Okay? In each case, there is a target graph, and the question is, does the input graph admit the homomorphism to the target graph? For K coloring, the target graph is KK, complete graph on K vertices. For the cyclic coloring, the target graph is a cycle. And for the multicoloring, or the, what do they call it? K-tuple coloring, the target graph is similarly a graph on pairs or tuples in which two vertices are adjacent, just that the tuples are disjoint. So in each case, you are just asking, is there a homomorphism to the target graph? So a homomorphism is a mapping which preserves adjacency. So just as I said, for the cyclic coloring, you want to assign to adjacent vertices consecutive colors. Now I'm going to say you want to assign to adjacent vertices adjacent images. Okay. Adjacent vertices obtain adjacent images. And so the previous examples then say K coloring is the homomorphism problem for KK. The cyclic coloring is the homomorphism problem for cycle. The T-tuple K coloring is the coloring problem for this special graph where vertices are tuples and only disjoint ones are adjacent. And in 1988, my classmate from Prague, Jarek Nešetřil, came to Simon Fraser on sabbatical. And we started thinking about this problem, looking at all these special cases, wondering whether you can say just for an arbitrary graph H, when you fix the target graph H, when that is polynomial and when that is NP-complete. And he stayed in my basement and we worked the whole year he was there, and we still just had some partial results and we were very frustrated. And he went back to Prague and we started communicating. He wrote letters back and forth and probably entertained the police censors who were opening letters at that time by these mysterious messages. But in the end, maybe 4 months after he left, we realized that, yes, we now sort of have a proof. We can give a dichotomy. And dichotomy is, if the fixed graph has a loop or is bipartite, then the problem is polynomial, and in all other cases, it's NP-complete. This is what we suspected from the beginning, but we didn't really have a proof until maybe 18 months since we started, 18 months of work. And just to be sure you see the reason that these two problems are polynomial, if a graph has a loop, target graph has a loop, and you get input any graph, then just map all vertices to the vertex which is a loop. Then adjacent vertices obtain the same image, and the same image is adjacent to itself, and so this is a homomorphism. And if a graph is bipartite, then there is a homomorphism if and only if the input graph is bipartite. So in both cases, the answers are really trivial. So the difficult part was to prove the problem is NP-complete. I should say at this point that although we were very happy to have solved this problem and eventually have written the paper, which is something like, I don't know, 35 pages long, we were sort of frustrated because, you know, we said we spent 18 months working on something no one else is interested in. And in the meantime, you know, tenure clock is ticking and you have to worry about having done good work. And that's where it dropped. Luckily for us, there was a very bright student of Dartmouth by the name of Thomas Feder, who was just finishing his PhD at Stanford at that time. And he did the smart thing. He put our result and Schaefer's result side by side and said, these two sort of look similar to me. And so let's see how far do I guess I have to say the spiel here. So in the first case, you have one symmetric binary relation, which is the graph H. But it's not on 0, 1, it's on the vertices of H. So you have only one relation, but the ground set is arbitrary. In Schaefer's result, you had any number of relations, but the ground set is only 0, 1. So again, play the difference, just the context, not the answer. The context in the first case is the target structure H has only one relation. The relation is binary and symmetric, but the set on which that relation is fixed is arbitrary. In Schaefer's problem, the set on which the relations are fixed is only 0, 1, a two-element set, but the relations are arbitrary, any number of any arities. And the answer is also sort of a little bit similar. Let's look at the first case in graphs. The problem is polynomial if there is a loop. What is a loop? That allows a constant mapping. Well, that's what the first Schaefer lines are, a constant mapping. What about the case when it's a bipartite graph? How do you check whether the input graph is bipartite? You say this vertex is 0. Then anything adjacent to it will be 1. Then anything adjacent to that will be 0, and so on. If that doesn't work, then there is no coloring because there is an out cycle, right? It's like two-sat. You say, if this variable is 0 and you have such and such clause, then that one must be 0 also, and that one must be 1, and so on. So the first case of loop is the constant. The second case of bipartite graph is the propagation. Schaefer had one more case, the algebraic case, which just didn't occur in graphs. So what Feder did, and then collaborated with Vardy on writing a paper about it, he said, let's play the game that Schaefer did, but not on 0, 1, but on an arbitrary set. So take a structure which has vertices and relations, and you take a finite number of relations of finite arities on those vertices. So I give you a set of vertices, and I give you on the set 1 ternary relations and 2 relations of arity 5. And then the problem is you have a similar structure, G, which is the input graph. Relations are in correspondence. And you are asking, is there a mapping that is compatible with all the relations, just like Schaefer did? So the only thing he generalized is the fixed structure doesn't have just 2 elements, but any finite number of elements. And so then our problem is okay, anyway, I will get to that. So they say the problem, constraint satisfaction problem on H, on this relational structure, is the input is a similar structure, any set on which there is 1 ternary relations, the relation, and 2 relations of arity 7, I think I said, so that they are in correspondence. And then you want to have a mapping which takes any tuple from the given structure in that particular relation to a tuple in the fixed structure in the corresponding relation, just like we did before. Now, this is called the constraint satisfaction problem because it's easily reformulated into language you might know from AI courses as the constraint satisfaction problem, where you have, variables and domains and constraints, and you are looking for an assignment of the variables that satisfies all the constraints. If you haven't had an AI course, then maybe this is irrelevant, but just explains the terminology. It can also be formulated in relational database as a relational databases problem. It's a very general problem. Books are written about it. Journals are devoted to it. Of course, what the books and journals do is look for practical solutions. You want this is a language in which many important problems can be formulated, and people are looking for good algorithms. There are companies that make their living on providing good software. All right, so here is the conjecture that Feder and Vardy came up with. If you have this CSPH problem, H is a fixed relational structure, and the problem is, given a similar structure, is there a compatible mapping? Then, okay, here I observe that when H has only 2 vertices, this is the problem of Schaefer. And when H has only 1 relation, then this is the problem that Neshetshil and I studied. Okay, the conjecture is this. Given any finite family of relations, the problem is either in P or is NP complete. So they say it's not a coincidence that you prove dichotomy for graphs and Schaefer proved dichotomy for binary or Boolean satisfiability problems. All these constraint satisfaction problems are either polynomial or NP-complete. That became known as the Federer-Vardy dichotomy conjecture and became a driving force of much subsequent work on trying to prove this, because it sort of directly contrasts and complements the theorem of Lardner that I mentioned earlier, which says if P is not equal to NP, then there must be problems in between of intermediate complexities. And this says in the world of CSPs, this doesn't happen. There are no intermediate difficulty problems for the constraint satisfaction world. I hear a voice. Yeah. Good. I can stop anytime. So I basically already said that. Let's skip the directed graphs. At this point, the important input came from universal algebra, where people study mappings that are sort of generalizations of homomorphisms. They're polymorphisms. They assign value to k-tuples of values from a structure. And it was discovered by Javens and his students and collaborators that the complexity of the problem CSP directly depends on the structure or quantity of these polymorphisms that the structure has. So basically, how rich is the polymorphism cone or polymorphism space of a structure decides how difficult the problem, the complexity of the problem is. If H and H prime are two structures, and H prime has the same polymorphisms H had and others, then H prime is a reduction to H. H is a harder problem than H prime. And that unlocked a decade of very important algebraic studies, which eventually in 2017 appeared in 2018, resulted in a breakthrough by independently by two Russian mathematicians in the West. One was my colleague Bulatov and the other was Zhuk. Andrei Bulatov and Vladimir Zhuk. And it turned out that there is one particular kind of this algebraic structure, polymorphism, that makes a problem polynomial. And if that particular polymorphism doesn't exist, the problem is NP-complete. So this was, I think, a big breakthrough in computer science. And I just sort of happened to ride the wave of this because our results were one of the two motivations for this conjecture and result. And I'll stop here. It's a good place to stop.
This is very nice. Why is it that why is it that, for example, graph response? It's kind of believed to be somewhere in the middle.
I think, it's not exactly the same. The thing that you have to realize here is that the target structure is fixed, right? If you don't fix the target structure, if the problem is given graphs G and H, is there a homomorphism from G to H? That's NP-complete, no big deal. If given two structures G and H, is there an isomorphism from G to H? It's a different question. That is sort of more structure to it, and that sort of easily could be polynomial or between. It could easily be between, right? There are problems that could be between. When Karp formulated the P equals NP question, There were problems that have since been resolved, like linear programming. He mentioned specifically, is linear programming polynomial or NP-complete? Yeah, and I don't know, primality testing and other examples that have since been shown polynomial.
This result been used to prove some problem with NP-complete? Like you told that a problem has this.
Definitely. No, if you find a weak polymorphism, the problem is polynomial. It's actually not easy to design an algorithm, but what is easy is to say if there is no weak polymorphism, it's NP-complete, and that has been used. In fact, I have used it in some papers where I want to see something is NP-complete and I just cannot be bothered to find the right thing to reduce to. And then I just say, okay, well, could there be a weak new polymorphism? And I try this, and obviously no, and then I have a proof. Definitely, it's a useful result from that perspective.